Welcome to the New Chemist podcast. We're glad you're listening. Feel free to download this podcast on Spotify, Google Podcasts, and Apple Podcasts. Here on the New Chemist, we discuss chemistry, which simply put is the science of change, as well as the other sciences, careers, community, research, and COVID-19. Good evening, students. It is so good, so exciting to have you in lecture today. It's definitely a privilege, an honor. It is a treat. Just want to remind everyone, you are not alone. This is an academic community. Remember to get help from university services if needed. Never give up. Never give up. Keep trying. We're here to help you be intelligent, successful, and responsible scientists. However, at the end of the day, you must be responsible, intelligent, and hardworking. I want to remind you, don't give up. It may be challenging, it may be hard. Find strategies, find resources, meet with people, network, do what you can. It's worth it. You are smart enough, you are good enough, you are worth the effort and the fight. Keep it up. So, today we're going to be going through a few advanced topics. I just want to give you a quick preview of some organic chemistry ideas. It's very valuable, very useful, and I think it'll be a good resource for you. This book was written by myself and reviewed by one of my good colleagues and friends, Vincent Miranda. So it's dedicated to the tens of people who have helped and inspired me, specifically my parents, Doctors Ferguson, my brother, attorney Ferguson, and my sister. It's definitely, and his wife as well, my brother's wife as well, and those teachers in university and high school who helped make science accessible to me. So let's just go over it. Organic chemistry is a subject that requires effort, focus, and skill. These foundations have been selected after guided review and observations as to what concepts facilitate and support a good understanding as a student progresses through this discipline in chemistry. These foundations, from the moiety to the metallics, highlight with conceptual focus key ideas, points, and memory aids to support your success in organic chemistry. Learning organic chemistry is similar to building a house. It takes time, skill, and persistent efforts. So let's begin. Of course, this will be an audio and a visual as well, depending on how you learn. The goal for this episode is to encourage those who are studying organic chemistry. I know from personal experience that organic chemistry can be at points, especially organic chemistry 1, challenging because you're adjusting to a new paradigm per se, and you are adjusting to a new set of content. But the thing you have to remember is with strategy and persistence, you can make it through it and do well and do your best. So, some objectives that we want to remember. We want to learn the key definitions. We want to understand key ideas and the relevance of lower start structures, and we want to understand some simplified quantum mechanical concepts. Organic molecules can be defined as multiple atoms associated or bonded together, made primarily from carbon. In short, organic molecules are carbon-based molecules. So we have the structure of cyanocobalamin. This is the structure I did my undergraduate thesis on, also known as vitamin B12. These molecules may or may not have the same molecular formula. In cases where the molecular formula is the same but the structure is not the same, you have structural isomers. Some examples include acetone and dimethyl ether. Note, when the constitution or the connectivity is not the same, you have constitutional isomers. Where the arrangement in 3D space is not the same, you have stereo isomers. In some instances, constitutional is sometimes interchanged with structural isomers. Now, subclasses of stereoisomers. You have optical isomers, which are molecules that rotate light differently, and their mirror images are non-superposable. Otherwise known as enantiomers, and they are designated by EZRS, Intagen, Zusammen, Rectus, or Sinister. geometric isomers, which are molecules that have non-identical mirror images. There has to be a cis and trans. And the arrangement around the plane of the double bond is different. Organic molecules can be linear. Linear molecular shape is observed with hydrogen cyanide or acetylene, or it may be planar, but trigonal, such as formaldehyde. A bit of formaldehyde, the structure for formaldehyde is cut off. The other hydrogen. Also, the molecule can have a 3D arrangement such as methane, existing as a tetrahedral molecule. So it's important to remember that molecules are multiple atoms bonded together, and compounds are a type of molecule in which you have multiple heteroatoms bonded together. So the atoms are different in that case. So let's talk about the structure of 3D molecules. The structure of 3D molecules can be predicted using an application of correctly drawn Lewis dot structures, which is valence shell electron pair repulsion theory, also known as Glepsin-ion theory. VSEPR, that's one way to say it, involves valence bond theory, showing all valence electrons and including bonding and non-bonding electrons, in some cases referred to as lone pairs, and maximizing separation in 3D space so as to minimize repulsions connected to Coulomb's law in the greater distance. In that greater distance minimizes potential energy, so greater distance between like charges minimizes potential energy, and the converse is true in that when you increase or decrease the distance between unlike charges, you also minimize potential energy. So VSEPR is an alternative that can inform and start the journey in us understanding molecular geometry, whether it be the linear alkynes, the trigonal planar arrangements of the carbon atoms in some alkenes, or the tetrahedral arrangement of carbon atoms around some carbon atoms in alkanes. Another alternative involves using quantum mechanics that uses wave functions that are mathematical descriptions of electron probability distributions to produce atomic orbitals. There are some limitations in this method as it pertains to accuracy, as with the previous method, VSEPR, considering the theoretical simplifications that I use. Overall, the goal is to gain a better understanding as to what occurs in nature. For example, with quantum mechanics, we can step into hybridization theory and use mathematical mixing of wave functions to further our understanding of what is observed in nature. With the same goal, through ideas like valence bond theory, we can predict the bond angles for methane, specifically the intramolecular H bond angle in methane, hydrogen bond angle in methane. There are deviations, however, that are observed, and hybridization accounts for those deviations with explanations. Those explanations entail the ideas that linear arrangements have carbon atoms that are sp hybridized, 1 sp plus 2 p's. Trigonal planar arrangements have carbon atoms that are sp2 hybridized, 1 sp2 plus 1 p. And tetrahedral arrangements have carbon atoms that are sp3 hybridized, 1 sp3 plus 0p. Other hybridizations occur less frequently in mainstream organic chemistry. However, with higher geometries common with inorganic compounds, there can occur trigonal bipyramidal sp3d or octahedral sp3d2. So note, quantum mechanics also involves the use of molecular orbital theory to understand other interactions, but that will be discussed later. With the same focus, quantum mechanics also enables chemists to speak on regional electron densities. Also, it's important to know that double bonds possess a sigma bond and a pi bond, and triple bonds have 1 sigma, 2 pi. So some questions you want to think about. What is organic chemistry and what is the historical origin of it? What is one class of organic compounds? What are 3 different types of isomers? Explain the valence bond theory in general simple terms. What is one molecular example where valence bond theory does not accurately explain what occurs in molecules? What are the hybridization of carbon atoms in acetonitrile? What are the designations of sigma and pi for the bonds of acetonitrile? So let's keep going. We're going to have a quick break and then we're going to continue talking about functional groups and other ideas. Okay, so let's go. Functional groups and other ideas. So you want to understand what is a functional group, understand the key format for organic nomenclature, and understand the role of intermolecular forces. Functional groups are characteristic parts of molecules that convey specific chemical properties to the molecules that possess them. Functional groups do numerous things, but mainly they enable us to compartmentalize information about molecules, compounds, and reactions. Functional groups do give us insight into chemical interactions, such as intermolecular interactions, as well as give us more information in understanding the properties of molecules. This includes the physical properties, boiling points and melting points, and solubilities. Considering the usefulness of functional groups, they also possess a characteristic molecular fingerprint that is detected in many ways, namely in spectra, so IR spectra, which really gives you a fingerprint as to the functional groups within a molecule, and that'll be discussed later. So case in point, we have an example of phenol right there. So we have types of molecules and their properties. There are several types of molecules in the world. However, in the discipline of organic chemistry, there are specific molecules that are discussed frequently, including these. You have your alkanes. Alkanes, otherwise known as paraffins, are saturated hydrocarbons and aliphatic compounds. These molecules form a series of homologs with a repeating methylene unit and with the general formula CnH2n plus 2 and ending with the suffix ane. For example, in increasing order from 1 to 5, we have methane CH4, ethane C2H6, propane C3H8, butane C4H9, pentane C5H12. The following prefixes are hex for 6 carbons, hept for 7 carbons, oct for 8 carbons, non for 9 carbons, dec for 10 carbons. These prefixes from meth to dec are applicable throughout the naming of organic compounds, alkanes, alkenes, alkynes, alcohols, etc. And there are lots of ways you can code this information, even when it comes to heterocycles, whether it be ir, et, dash, ep, ir, et, dash, ep. So there are lots of ways you can code the information for different heterocycles. We can discuss that chunking on that mnemonic later. So ir, oxirane, oxetane, oxane, oxalane, oxeptane, all those things. We can discuss that later. So alkenes, otherwise known as olefins, are unsaturated hydrocarbons and they are considered aliphatic compounds. They contain at least one double bond, forming a homologous series with the formula CnH2n. These are alkenes now. These molecules end with the suffix -ene. So alkynes, otherwise known as acetylenes, are unsaturated compounds having a triple bond. These molecules form a homologous series with a general formula CnH2n-2. These molecules end with the suffix -ine. There are several other molecules that form a homologous series within their groups, including carboxylic acids and aldehydes. You also have alcohols. Alcohols whose main functional group for identification is the hydroxyl group. It is notably priority in nomenclature practice. Exceptions include carboxylic acids according to the IUPAC. Alcohols contain one or more hydroxyls forming a homologous series, CnH2n plus 1 OH. Alcohols are aliphatic and typically end with the suffix -ol. So let's talk about intermolecular forces and other properties. With functional groups comes certain properties such as specific boiling points and melting points, as well as critical temperatures. The temperature around which a vapor does not easily undergo a phase change to a liquid, and many other physical properties. However, beneath the surface of physical properties are the chemical features or interactions known as intermolecular forces, which influence and enable comparative predictions and physical properties. Namely, there are key forces to remember. You have your dipole-dipole forces. These are forces which occur between molecules, intermolecular, with a dipole moment or a significant dielectric constant. These molecules are otherwise known as polar. These intermolecular forces, IMFs, are relatively strong. A relatively stronger version of this is the H bond or hydrogen bond intermolecular force. So you have your hydrogen bonding. It is a stronger force, sometimes referred to as a strong dipole-dipole force. This is a relatively strong, some consider it strongest, of the IMFs. It occurs in water and other molecules with hydrogen bonds to nitrogen, oxygen, and fluorine. Then you have your ion dipole. This occurs between ions and polar molecules, for example with solvation of sodium chloride crystals in water. Then you have London dispersion forces. London dispersion forces occur in all molecules and are based off of the Coulombic interactions between transient, in essence temporary, dipoles. These electrostatic forces result in transient interactions between molecules. Then you have van der Waals forces. Now a weak force that consists of two kinds, including the van der Waals force, which is discussed in short, is where more elaboration can be found in other texts, in other episodes. It is worth noting that IMFs and their strengths are based off of functional groups, chemical structure, and the types of chemical bonding in those molecules, so intermolecular bonding. So what's inside influences what occurs on the outside. Composition influencing function. Anyway, chemical bonding, you have polar covalent bonding. Covalent bonding occurs between atoms with significant electronegativity differences. So this is polar covalent bonding. Specifically, this bonding occurs with heteroatoms, which refers to different non-metal atoms. So different non-metal atoms. Many times the Pauling scale is used as a reference for ranges to determine the type of bonding arrangement occurring between atoms. If bonding, though considered a theoretical construct, is viewed on a spectrum, polar covalent bonding would exist around the middle. Then we have covalent bonding. This is also non-polar covalent bonding. This is almost at the another end of the bonding spectrum, where there is less significant difference in electronegativity. So then you have ionic bonding. This is at the other end of the bonding spectrum. This occurs between metals and non-metals. For example, in sodium chloride, there's a large difference in electronegativity. Solvation. Solvation is dependent on many factors, including the principle like dissolves like, and ideas such as hydrophilicity and hydrophobicity. Hydrophilicity and hydrophobicity. These terms refer to the molecule's stance in relation to water, whether it has a significant affinity for water, hydrophilic, water-loving, or less significant affinity for water, hydrophobic, water-hating. The tendency of molecules is as follows. Polar and ionic compounds tend to be hydrophilic compared to covalent and non-polar compounds which tend to be hydrophobic. Nomenclature, according to the IUPAC, is based off of four main parts: prefix, locant, parent chain, suffix. The prefix, this normally denotes the number of each substituent or functional group attachment. Prefixes include di, tri, tetra. The locant, which is the number that describes the functional group attachment or the substituent's position. The parent chain, this is normally the longest continuous chain in the molecule. The suffix, this is based off of the presiding or prioritized functional group, chain, or bonding arrangement, single, double, or triple. Suffixes are typically classical in ending, with ane referring to your alkanes, ene referring to alkenes, ine referring to alkynes, amine, amines, amide, amides, oic, carboxylic acid, ate, esters, one, ketones, dehyde, aldehydes. Key facts to note: the alcohol's functional group hydroxyl is normally prioritized overall. Substituents are transcribed or outlined in the name based on the relative alphabetical order, so ethyl before methyl, and that pattern continues. So key overall idea, and I'll repeat this twice. Prefix, locant, parent chain, suffix. Prefix, locant, parent chain, suffix. Prefix, locant, parent chain, suffix, generally. So you can look up further ideas about IUPAC nomenclature in other texts. So some questions to consider. What is a functional group? And name several examples of functional groups. What are 3 types of organic molecules? What is an intermolecular force? Explain dipole-dipole forces. What is one molecular example where intermolecular forces explain a physical property such as boiling point? What is one difference between hydrogen bonding and London dispersion forces? Explain the overall process of naming simple organic compounds. So if you want, just an aside, quick aside, you want more information into heterocycles, there's a phenomenal chemist, his name is Dr. Barron. He has lots of resources out there for heterocycles. So feel free to look into that. Very good resource, very brilliant chemist. So let's keep going. Concept development 3, structures, conformations, and projections. So one things we want to do, and also just remember this episode is primarily dedicated to those in general chemistry as well as those who are in organic chemistry, with the thrust that we want to encourage and help each other as we go along in our scientific careers. So, objectives: understand and be able to draw Lewis electron dot structures, condensed structures, and bond line structures. Understand and be able to draw different conformations, primarily those of cyclohexane. Understand and be able to draw and identify Fischer projections and Newman projections. So structures are diagrammatic representations of different molecules, and they provide a means of understanding what is occurring in nature. There are a variety of different structures used in chemistry. The main examples in this episode would be Lewis electron dot structures, condensed structures, and bond line structures. So Lewis dot structures, named after your boy Gilbert N. Lewis, a brilliant scientist. They are built on some key ideas such as the Adams valency and the octet rule. There are specific exceptions for period 3 with sulfur and arsenic, for example, and beyond. Valency. Valency refers to the amount of electrons an atom will lose, many times resulting in a positively charged ion cation. Gain, many times resulting in a negatively charged ion anion. Or share, typically occurring in covalent molecules, in order to have a stable noble gas configuration. Ground state, of course. Valency can be determined using the periodic table. The group number, the vertical column numbers for main group elements typically in the periodic table is designated the valency. The valency corresponds normally with charge, oxidation number, and its subsequent sign is dependent on the type of atom, its reactivity, and what it is reacting with. So, key points to note. Valency can be shown quickly using Lewis dot structures and orbital arrangements. Can be explained simply, in some ways, with the Bohr model. The octet rule now. The octet rule is a principle with applications in resonance theory, simple chemical mechanisms, and reactions. The octet rule is based on the idea of atoms gaining, sharing, or losing electrons in order to have a complete octet. And in this context, we're referring to 8 outer electrons. There are exceptions. For example, some atoms may lose electrons to possess the electron configuration of helium, 2 outer electrons. However, for the most atoms, in period 1 and period 2, in the periodic table of elements, those elements obey the octet rule generally. This rule is helpful in predicting reactivity and explaining simply the rationale for certain chemical reactions. So from period 3 onward, there are exceptions. So let's think about the rules for writing Lewis electron dot structures. So NP-SEM, note the total amount of valence electrons. Place single bonds between each atom. Subtract 2 electrons for every single bond added. Eliminate or note the remainder amount of electrons. And minimize formal charge as best as possible. So for atoms and ions, consider the group number primarily an electron configuration. For molecules, start by determining the total electron count among the atoms in the molecules. Draw single bonds between each atom. Subtract to electrons for each single bond, add extra bonds when necessary. For example, carbon-oxygen bonds in aldehydes and ketones. Bonding arrangement is typically in the form of a double bond. Ladies and gentlemen, you must know and observe the trends. After all the necessary extra bonds have been denoted, subtract the correct amount of electrons for the extra bonds added. Typically, with the remaining electrons, denote them as lone pairs around the relevant atoms. So let's keep going. Condensed structures. Condensed structures are important in the process of understanding what bond line structures represent and show. In condensed structures, all of the hydrogen bonds are attached to the carbon. For example, S2 bromobutane, you can see here. So bond line structures are the next step after condensed structures. These show only the carbon framework with each carbon represented by a bend in the chain, and the hydrogen not denoted, but inferred or assumed to the point or a complete octet around the carbon atom. This means the hydrogens are not shown, but implied to the point that the valency of carbon is satisfied. For example, we see there, bond line structures are useful and efficient. They save time. You can see an example of a bond line structure right there for benzene. Now conformations. Conformations are molecules that differ only by rotations around single bonds. You may have heard of conformers, rotamers, otherwise characterized as sigma bonds. These alternate rotations affect the potential energies of the molecules, either increasing, as seen in the eclipse conformation, or decreasing it, as seen in the anti-conformation. Conformation's potential energies are attributed to ring strain, which is based off of the angle strain and the torsional strain. Angle strain is caused by the alternate bond angles that have deviated from the idealized bond angle suggested in VSEPR. Torsional strain is caused by repulsion due to the dispersion forces, an intermolecular force, and this can cause steric hindrances. So as you progress further in your career in science, you'll hear the two whistling concepts, two echoing concepts in the halls of organic chemistry. You have sterics and electronics. So conformations can be experimentally described using a graph of dihedral angle versus potential energy. As you study this some more, you encounter things like Karplus correlation, all of that a lot of good stuff. So typically cyclohexane is plotted showing the potential energy of the different conformations in there or in increasing potential energies. The chair, the twist boat, the half chair, and the chair. Chair, twist boat, chair, half chair, twist boat, half chair, chair. It's important when you start learning about this to be able to draw your chairs correctly. Chair, half chair, twist boat, twist boat, half chair, chair. So CHT, BTHC. CHT, BTHC. Chair, half chair, twist boat, twist boat, half chair, chair. Projections. In chemistry, there are many types of projections. However, two that are frequently encountered are the Newman projection and the Fisher projection. So Newman projections are structures from a specific perspective. We look down a specific single bond between atoms and draw the other attachments in respect to those two atoms. For example, butane is drawn. So picture yourself looking down the axis of a single bond, C2 to C3 of butane, or C2 to C3 in some other molecule. In order to draw the Newman projection. Here we see an example of Newman projection. Then you have your Fisher projections. These are typically seen with your carbohydrates and your hexoses and all those other good stuff. They involve another representation from a different perspective. The molecule is drawn from top to bottom, normally with the anomeric carbon at a designated end. Generally, the functional group attachments are on the sides, which are seen as wedges that are out of the plane of the paper, and the top and bottom of the projection is seen as groups on the dashed. Another bond designation uses a squiggly line which represents a single bond out and behind the plane of the paper. So the projection is typically used with carbohydrates, especially simple carbohydrates. So you can see an example of R, 1 bromo, 1 chloroethane, and then you can see another example of thalidomide. Plastic molecule, as is also discussed when we introduced the key ideas associated with stereochemistry and how important it is even when it comes to medicines and their use and effects in the human body. So let's talk about some questions. What is the lowest electron dot structure of oxygen? What are the key ideas for drawing Lewis electron dot structures? Explain the concept of valency. Explain the octet rule. What is one exception to the octet rule? Draw the bond line structure of antizine. Explain the overall order of stability for cyclohexane conformations. Remember, we go chair, half chair, twist boat, chair, half chair, twist boat, boat, twist boat, half chair, chair. Chair, half chair, twist boat, boat, twist boat, half chair, chair. CHTBTHC. CHTBTHC. For those who need to know that. Okay, so let's talk about chirality and isomerism. You want to know key definitions. Definitions of words such as isomer, chiral, and conformers. Understand the concepts of stereoisomerism, chirality. Understand the Lebel and Van Hoff rule. So let's keep going. Isomers, as defined earlier, are molecules with the same molecular formula but different in structural arrangement, space, connectivity, or geometry around the bonding arrangement. All those differences aforementioned define a subclass of isomers, be it structural, so structural isomers, arrangement in space, stereoisomers, or connectivity, constitutional isomers. Each subclass has its own significance. Stereoisomers or spatial isomers are molecules with the same molecular formula but different three-dimensional spatial arrangements. A stereoisomer has a stereogenic center, which is a location in the molecule where the interchange of two groups in space results in a new stereoisomer. A subgroup of stereogenic centers is a chiral center, which typically refers to a stereogenic center with a sp3 hybridization or tetrahedral geometry. Every chiral center is a stereogenic center, but not every stereogenic center is a chiral center. Stereoisomers can be further divided into other categories such as enantiomers, non-superposable mirror images, diastereomers, non-identical mirror images, atomizomers, isomers as a result of restrictions in bond rotations. So enantiomers are optical isomers. These optical isomers are molecules that are non-superposable. Enantiomers typically have chiral centers, or a chiral center. Enantiomers are very significant in the pharmaceutical industry, with specific enantiomers in drugs having specific effects. This is seen with the classic example of thalidomide, ibuprofen, and Darvon, where stereospecificity contributes a large role in determining therapeutic potential and therapeutic effects. Enantiomers are typically designated by the signets of absolute configuration, which are R rectus and S sinister. Mixtures of both enantiomers are called racemic. Usually these are mixtures of equal proportions. The process of forming both enantiomers as products is known as racemization. And if you do some more research, you'll hear about Viedma ripening. You can do the research and find out about it. So the molecules are also designated by the relative configuration, which are dextrorotatory D and levorotatory. And that refers to their optical rotation, how they rotate light. So let's talk about assigning configurations. Dextrorotatory or levorotatory must be assigned experimentally, typically by the proper application of an optical device such as a polarimeter. To observe and measure how the molecule rotates light and to what extent or degree it rotates it. Absolute configurations can be assigned using a priority numerical labeling system such as the Kahn-Ingold-Prelog priority rules. These rules give priority based on atomic mass. Larger atoms have the highest priority, and the smallest or least weighing atoms have the least priority, typically hydrogen in most molecules. So if you have hydrogen, typically it's going to be on the dash. Okay, in the back of the plain of paper. And then your largest priority, thing that has the highest priority, is going to be coming out at you. Okay, so there you have S1 bromo 1 chloropropane. So let's talk about diastereomers. This is a subclass of optical isomers. A subclass of optical isomers, known as geometric isomers. Diastereomers are isomers with the same molecular formula but different arrangements in space. That results in non-identical mirror images. These can typically be identified by first assignment of the absolute configuration of the stereogenic centers, then comparison of the mirror images to determine whether they are identical or not. So that's a suggested way you can do it. Subclass of diastereomers are cis-trans isomers and conformers, which can further be divided into rotamers. So you have your easy isomerism and your cis-trans isomerism. As dexteratory and lever rotatory is relative assignment for stereochemistry, so is cis and trans. Cis and trans isomerism allows for the denoting of the spatial arrangements based on like groups, for example, trans 1,2-dichloroethene or cis 1,2-dichloroethene. This relative system, cis or trans, can become obscure very quickly. So to provide a more meticulous system, the Kahn-Ingold pre-log priority rules are used to label the substituents on the double bond using entagon, E or opposite, and zusammen or same side. So entagon, E opposite, zusammen, same side. This system aforementioned provides more clarity with stereochemistry. As stated earlier, the Kahn-Ingold pre-log priority rules give the highest priority to the largest substituent or the substituent with the greatest atomic mass, and the following substituents are labeled with the numbers 2, 3, 4 based on atomic masses. So you number your substituents. Basically, you assign your priorities, you number your substituents. It's good to do this with your modeling kits, your modeling sets, and if you can't afford it, you can use gumdrops and toothpicks. And just make sure you use different colors for different types of atoms. But assign your priority, arrange it, visualize it in 3D space. You may have to build a model. And from there, you see 1, 2, 3, 4. Rectus, 1, 2, 3, 4, sinister. If it goes clockwise, if the substituents are ordered such that they go in a clockwise way, rectus. If they go or they're arranged such that they follow a anticlockwise path or trajectory, we call it sinister. So conformers and rotamers. A conformer is an arrangement or conformation of a molecule based on rotation of single bonds that resulted in a potential energy minimum. A classic example of a conformer is with cyclohexane, which you have different conformers represented in the graph below. A rotamer is just a conformation of a molecule that results from another rotation of a molecule's single bonds. And you have the anomers, automers, and isomer formed due to the geometric variation found in certain atoms in specific molecules. Anomers are typically seen and described in carbohydrates where the designation of alpha or beta is used. Alpha D-glucopyranose, beta D-glucopyranose. And you have the epimers. An epimer, normally found in diastereomeric pairs, is a stereoisomer that differs in configuration at any point in the molecule where changing the position of the two substituents results in the formation of a new stereoisomer. Basically, an epimer is an isomer that differs in configuration at any stereogenic center. So Libelle-Van 't Hoff rule. If there are n stereogenic centers with 4 different substituents attached, there are 2 to the n different stereoisomers possible. So if you have n stereogenic centers, there are 2 to the n different stereoisomers possible. Okay, so some questions to think about. What is an isomer? What are the different types of isomers? Explain the concept of enantiomers. What is a racemate? And even further research, you can look into what is V-amer ripening. Then you can talk about, or just look into what is a diastereoisomer. What are 2 subclasses of diastereoisomers? And then we can talk about explaining the Kahn-Ingold-Preller-Pardee rules for designating absolute configuration. So let's keep going. Nucleophilicity and electrophilicity. In it for the long run. Learn the definition of nucleophilicity and electrophilicity. Understand the trends with nucleophilicity and basicity, or electrophilicity and acidity. So we want to understand those things. Those are our objectives for this reading. Nucleophilicity is a kinetic concept that describes the affinity of an atom or molecule for the nucleus of another atom, which is positively charged with the intended meaning of nucleus loving. So nucleophilicity, nucleus loving. This term is very important for understanding reactions and their mechanisms. Nucleophilicity refers to how willing, to what degree, or at what rate is an atom or molecule donating its electron density to another atom or molecule. The degree of nucleophilicity is defined by the rate of the reaction, specifically the rate of electron density donation. Generally, nucleophilicity, when comparing a similar atom in multiple molecules, follows Lewis basicity for some contexts. Also, when a nucleophilic atom is different, there may be no relationship between nucleophilicity and basicity. So that's something to note. If the nucleophilic atom is different, there may be no relationship that you observe. Since dipole moments for each atom or molecule may be different, thus affecting polarizability, which is a large determining factor in nucleophilicity. So polarizability of the electron cloud is a large determining factor in nucleophilicity. So it's very important to understand it. It's grounded in Coulombic. It's grounded in Coulombic forces. It can result in the formation or breaking of bonds, as seen in the infamous nucleophilic attack and nucleophilic substitution. So let's talk about electrophilicity. Electrophilicity is a kinetic concept. It involves a reaction in which there is an acceptance of an electron pair. An electrophile is defined as an electron pair acceptor, or an atom or molecular part that is electron loving, electrophile. This term provides insight into mechanisms or reactions such as electrophilic aromatic substitution, electrophilic substitution, and electrophilic addition. Electrophilicity it basically involves the measured degree or extent, kinetically speaking, of how much an atom or molecule is willing to accept electron density from another atom or molecule. So, some questions to consider. What are some key ideas associated with the concept of nucleophilicity? What are some key trends with nucleophilicity? Explain the connection between Lewis basicity and nucleophilicity. What is the connection between Lewis acidity and electrophilicity? Explain the significance of pKb, some aspects of the concept of nucleophilicity. So let's talk about spectroscopy and some instrumentations. Spectroscopy involves the study of the interactions of electromagnetic radiation and matter. Spectroscopy has a key role in organic chemistry. It contributes to informing many processes, including retrosynthetic analysis, structure elucidation, and total synthesis. Spectroscopy and spectrometry are different. Spectroscopy refers to the study of the interaction of electromagnetic radiation and matter, while spectrometry refers to the measurements of the interaction of electromagnetic radiation and matter. So measurements versus just the study. We have UV spec. As an example of a diagram, UV light source going to your scanning monochromator, a UV motor that's spinning, it goes to the sample cuvette, and you go to your detector, you amplify it, and then it's displayed. For your sample cuvette, you also have a reference cuvette as well. So UV-vis spectroscopy is an analytical technique that involves the use of ultraviolet or visible light in order to analyze a sample in a cuvette. This technique can be used to quantify, detect, test, support structure elucidation, and aids in determining molecular geometry and to study the kinetics of reactions. So when you think of UV-vis spec, also think about Woodward-Hoffman rules. One of the main ideas behind the use of UV-vis spectrophotometers is the principle of absorbance. You can look into Bayes' law, and also you can look into Bayes' law. Absorption is equal to epsilon molar absorptivity absorptivity constant, B. Path length, C. concentration. Then you have atomic absorption spectroscopy. AAS, go from your light source to your sample to your detector to your computer. It has many uses involving clinical, geological, biological, metallurgical, atmospheric, and also in the pharmaceutical industry. Then you have your IR spec. You go from your Nernst glow, this is just a version of it, to the Michelson interferometer, to your sample, to your detector, to your computer. So IR can be used to detect the functional group moieties that exist in the sample, the relative location or proximity of the information, the relative location or proximity of functional groups. That information can be obtained. It's based on the assumption that atoms behave as simple harmonic oscillators, that each vibration is occurring within the molecule. You have your NMR spec, in which you go from your RF radiation generator to your NMR tube, to your RF receiver, to your computer. NMR spec provides information on the chemical environment the nuclei of atoms are situated in. This type of spec is normally used in structure elucidation and in some cases structure determination. This analytical technique involves several concepts, some such as shim and all this other good stuff. So gas chromatography, mass spectrometry, you have your GCMS, you go from your sample holder to your capillary column, to your electron ionization, to your ion trap, to the computer. It's an analytical technique that involves both analytical techniques of gas chromatography and mass spectrometry. This is a method in which components of a mixture are separated using chromatography and analyzed and characterized using mass spectrometry. Gas chromatography is a separation technique in which chemical substances are volatilized and separated by their relative boiling point, which is dependent on the chemical properties of the molecules. Mass spectrometry is an analytical technique that involves the ionization of chemical species into different ions of different atomic masses and the sorting of ions into a unique spectrum based on their mass to charge ratio. So some key features are, what are some key features of a UV-vis spectrometer? What are some key features with the infrared spectrometer? What is the Jacquinot advantage, so throughput advantage? Explain Felget's advantage, multiplex advantage. Explain the differences between polar and non-polar compounds in the GCMS instrument. So we can talk about inorganic and organic metallics. This is the first part. Diatomic halogens have chemical significance as seen in several areas of organic chemistry. Whether in the presence of light, organic solvent, or peroxides, they can result in the formation of halogenated variable groups, which can vary from alkyl halides to acyl chlorides. Diatomic halogens, when substituted in the organic molecule, can result in new properties, both chemical and physical, stereochemistry, intermolecular forces, as well as conformations. Also, the chemical reaction environment also affects radioselectivity in the reaction. Also, diatomic halogens can be used to test for the presence of olefins, namely bromine methanalkene, and the result is a colorless solution. Diatomic halogens have versatile use in organic chemistry. So, several inorganic reagents are used as reducing agents or oxidizing agents to convert carbonyl-containing compounds in primary and secondary substituted hydrocarbons to primary and secondary alcohols, and in another direction it can convert alcohols to carboxylic acid. You have your sodium borohydride, used to do a stepwise reduction from aldehydes to ketones to alcohols. You have LiALH for lithium monohydride, very dangerous, flammable and powerful reducing agent that reduces carboxylic acids and other carbonyl containing compounds to alcohols. You have PCC, pyridium chlorochromate, which is used to oxidize. It functions to oxidize primary alcohols to aldehydes and secondary alcohols to ketones. Pyridium chlorochromate is made by reacting chromium trioxide with hydrochloric acid to form chlorochromic acid, which is reacted with pyridine to form PCC. Then you have the Jones reagent. It is an inorganic reagent that is used to oxidize. It functions typically as chromic acid and involves oxidizing primary alcohols to carboxylic acids and secondary alcohols to ketones. The Jones reagent is a good oxidizing reagent. Then you have KMnO4, potassium permanganate. There's another inorganic reagent that results in the oxidation of primary alcohols to carboxylic acids and secondary alcohols to ketones. Always remember or consider the temperature at which that oxidation is occurring. Very important. Then you have PCl5, a molecule with many uses, namely the interconversion of carboxylic acids and acid anhydrides to acyl chlorides. Then you have sodium cyanoborohydride. It is used in reductive amination, resulting in the formation of amines from the reduction of the cyanide portion of the reagent. There are some rearrangements that occur when this is taking place. This is another example of nucleophilic attack occurring. Meanwhile, sodium borohydride is serving as the infamous reducing agent. So some organometallics, you have your Grignards. Grignard reagents are some of the first encountered organometallics for an undergraduate organic chemistry student. These molecules are composed of an organic variable group, a magnesium atom, and a halide. These are normally used to attach organic variable groups to a carbonyl, meanwhile reducing the oxygen to a hydroxyl, thus making an alcohol. Grignard reagents are very useful, however, because these are reactive even with water. All material used in the reaction to avoid water contamination must be lab oven dried. Then you also have Gilman reagents. Gilman reagents are organocuprates attacking as a nucleophile to rings with an unsaturated region, alkenyl, or to an alkyl halide to form an alkyl substituted molecule. Then you have your regular nucleophiles such as metallic alkoxylates such as sodium ethoxide, magnesium ethoxide, which are used as nucleophiles to attack a variable group whether in an SN2 or E2 manner, as well as in displacement reactions. So, here are some questions. What are some examples of substitutions using diatomic halogens? What is an example of an oxidized alcohol? Explain the use of sodium borohydride in reduction reactions. Where does the organoborane occur in the reaction schema, and why is this chemically significant? Can nucleophilic attack serve as a means of oxidation or reduction? So let's talk about some regiochemistry principles. Understand the fundamentals of regiochemistry. Understand Markovnikov's rule and anti-Markovnikov's rule. So Markovnikov's rule, he who has more gets more. Anti-Markovnikov, he who has more gets less. Understand Zaitsev's rule and Hofmann's rule. So let's keep going. This will be the last section that we go through today. More to come later on. So regiochemical principles regiochemistry comes from the Latin word regionum, meaning direction. Regiochemistry provides and describes the principles involved in the directionality or position and placement of reactants to form the product. Regiochemistry is very important. As you progress, you'll hear about things being regiodivergent or regioselective. Reagents used can cause a specific regiochemical result or result in the opposite of what would normally occur. So you have Markovnikov's rule. Put simply, he who has more gets more. Markovnikov's rule is in the addition of a halide to an unsymmetrical alkene, the hydrogen goes to the carbon with the greatest number of hydrogens, and the halide goes to the other carbon. In another way, this rule states that the halide adds so as to form the more stable carbocation intermediate. Then you have your anti-Markovnikov, which is the reverse, he who has more gets less, in which the carbon with the greatest number of hydrogens does not receive the hydrogen but the most electrophilic portion of the molecule. For example, in hydroboration oxidation, in the presence of peroxides, the borohydride adds to the less substituted carbon of the hydrogen, and the hydrogen adds to the more substituted carbon. Keep in mind hydroboration oxidation, which this is done in the presence of peroxides. Or in this case, we're referring to it being done in the presence of peroxides. However, the stability comes about because the electron density shifts. This is one way to describe the mechanism. The electron density shifts to the electrophilic borohydride, resulting in it possessing a partially negative charge, the more substituted carbon possessing a partially positive charge. This is indeed stable due to the electron density during the incapacity of the alkyl group. In the discussions, we can talk about hyperconjugation. As character and the orbital overlap of the alkyl carbon. The alkyl group with the alkyl or electron-donated substituent provides stability. So, Zaitsev's rule. Zaitsev's rule is the directionality principle in which the more substituted alkene is favored through the use of a small base such as ethoxide. Zaitsev's rule is significant and aids in predicting products in elimination reactions. So Zaitsev's small base used to the more substituted alkene. So Zaitsev's small and more substituted. So Hofmann's rule. Hofmann's rule is another directionality principle. So T. Hofmann, in which the less substituted alkene is favored through the use of a huge or large base, such as tert butoxide. Hofmann's rule is also very significant and aids in predicting elimination reactions. So the Hamann-Leffler postulate. In simpler terms, it's basically the view on the potential energy hill continues in some ways as you follow through the potential energy journey, or the product resembles the molecular arrangement of the transition state, or the step of the RCD, the reaction coordinate diagram, that's closest to the transition state in energy. Typically, the transition state will resemble that. So what does the word regiochemistry mean? Was an example of a reaction that follows Markovnikov's rule. Explain anti-Markovnikov's rule. What is Zaitsev's rule significant? Why is it significant in elimination reactions? Explain the significance of the Hamann-Leffler postulate. Why are regiochemistry rules helpful in studying mechanisms? So types of reactions. Let's just go through these. You have your addition, substitution, elimination, reduction, oxidation, and rearrangement. Addition, put simply, is like a traditionally synergistic relationship. The two parts become one. Two different molecules are added together. Addition can be driven by nucleophiles, nucleophilic addition, or electrophiles. This type of reaction normally occurs in regions of high electron density and bond order, which is seen in compounds with multiple bonds. You have your substitution. Substitution is by definition a type of chemical group replacement. This can be driven by nucleophiles or electrophiles, as well as it can involve alkyl halides or aromatic compounds, SN1s, SN2s, typically some of the first reactions encountered by an undergrad in OChem. Then you have eliminations. Eliminations involve the loss of a group of atoms from a molecule. This can result in the formation of an alkene or alkyne product. Elimination tends to result in a net increase of electron density for a particular molecule, which, if considered, makes sense, since the overall process of loss and gain of electron density is usually presented mechanistically. Then you also have reduction and oxidation. Classically paired process in which one atom or molecule gains electron density while another loses electron density, which is reduction and oxidation, respectively. So oil rig, oxidation, loss of electrons, addition of oxygen, removal of hydrogen, increase in oxidation state or number. And then GLAD, gaining of electrons. Reduction is GLAD, oxidation is Larry. Reduction, GLAD, gain of electrons, loss of oxygen, addition of hydrogen, decrease in oxidation state or number. So you have reduction occurs in organic reactions such as hydrogenation using uranium nickel or lithium hydride. Then you also have your rearrangements, which typically occur through your 1,2 methyl shifts or 1,3 methyl shifts or 1,2 hydride shifts or 1,3 hydride shifts. The thermodynamic basis and rationale for these rearrangements occurring is that they lead to a more stable carbocation as a transition state or reaction intermediate. Many times the rearrangement results in positive charge being situated on higher substitute carbons. This is presented as secondary or tertiary carbons. There are other categories for mechanistic classification. Polar under basic conditions. Example is a nucleophilic substitution under basic conditions. Polar under acidic conditions. An example is an acid catalyzed hydration. Sorry about the background noise. You have paracyclic, an example is the 4+2 cycloaddition. Deals all the reaction. The 4+2 reaction refers to the number of electrons, specifically pi electrons. And you can look into Huckel's rule, each atom. So cyclic planar, each atom sp2, and it must follow Huckel's rule, 4n+2 pi electrons. So if your free radical reactions, example is the free radical polymerization, metal mediated reactions. An example is the sodium metal mediated Birch reduction. So some questions as we conclude. What are the key features of a substitution? What are the key features of elimination reactions? Explain the significance of rearrangement in terms of stability, and why is it important to know these types of reactions listed in this concept development. So later on, we'll discuss different types of substitutions and different types of eliminations. But I want to remind everyone, you're not alone. We are all in this as a scientific community. Reach out to people if you need help. Get the help that you need. Strategize, plan, use the resources at your disposal. You can do it. People are rooting for you. Keep up the good work. Glad to see that you're doing well. Hope everyone's doing well. And this ends this episode of Lecture Chaos.
Uma adaptação de um conto de fadas, A Dança dos 12 Princesas. Era um tempo lá como um professor que tem 12 príncipes nomeados. Namil, Estructuril e seu irmão Reactivil, Acidil e seu irmão Basicil, Nucleofilicil e seu irmão Electrofilicil, Equilibril, Estereochemico, Esterico e seu irmão Eletrônico e Regioselectivil. Cada príncipe era mais complementar do que seu irmão. Todos eles ficaram juntos na cidade mental chamada Orgânico-Chemico. Uma noite, durante uma semana mística conhecida como Finale, todos se reuniram para competir nos jogos anuais. Namil era notoriamente uma pessoa política que votou no PLPS, também conhecido como Principal Locante Parente Chain Sufixo. Estructuril competiu na competição de dança mostrando suas rotinas em suas formas condensadas e de linha de ligação. Reactivil participou da competição de pista principalmente na corrida chamada Kinetic 500. Acidil e Basicil competiram na competição de meditação liderada pelo Dr. Bronsted, que se concentra em obter e liberar seu próton interno. Nucleofilicil e Eletrofilicil ajudaram a organizar o Kinetic 500, enquanto ambos disputavam a competição de ginástica com Nucleofilicil se alongando ao máximo e Electrofilicil servindo de apanhador para os líderes da torcida. Equilibril participou da competição anual de esgrima de Le Chatelier. Além disso, Estereoquímico participou do concurso de arte com foco em desenhos 3D e disposição dos objetos no espaço. Estérico e Eletrônico sendo rivais ferozes. Competiu na competição de remo com vitórias estéricas em pontos e vitórias eletrônicas em pontos. A regata ainda está em andamento. Regioselectivil competiu na prova de leitura de mapas por ser bom em prever as direções das batalhas e a direção das caminhadas e viagens. Esses príncipes ainda competem hoje, e a história continua. Prefácio. O tempo e o acaso acontecem a todos nós. Depois de trabalhar e dar aulas particulares na graduação e receber uma bolsa integral para a pós-graduação, este livro é oportuno e um exemplo de retribuir para que outros se beneficiem. De fato, se você está na faculdade, estudando química, este livro apresenta uma oportunidade de ajudá-lo em seu sucesso como um guia complementar. Se você optar por usá-lo, lembre-se dos conceitos, use o próximo livro de exercícios e use métodos diferentes para um reforço positivo saudável. Os objetivos dos mnemônicos incluem aprender as versões simplificadas dos conceitos, não tecnicismos pesados, que em muitos casos têm ou terão exceções. É verdade que a repetição e a prática ajudam a reforçar os conceitos que você está aprendendo. Você consegue. DJF. Biografias de autores. David Ferguson. David Ferguson é um aluno de pós-graduação que recentemente recebeu uma bolsa integral para estudar química. Ele frequentou o Georgia Institute of Technology e a Taylor University, onde se formou com honras. Ele esteve na lista do reitor em ambas as instituições e recebeu várias bolsas de estudo enquanto estava na Georgia Tech e na Taylor University. David Ferguson fez pesquisas com o Dr. C. Aines no Georgia Tech Research Institute, bem como com o Dr. Daniel King e o Dr. V. Shula na Taylor University. Ele aspira a servir na academia e ajudar a ensinar e orientar futuros alunos em ciências após terminar a pós-graduação. 2. Vicente Miranda. Vincent Miranda é um estudante sênior de pré-medicina na Taylor University, trabalhando em um diploma de bacharel em bioquímica. Ele recebeu o prêmio de aluno mais destacado em química orgânica, bioquímica e química inorgânica na Taylor University. Ele também ajudou o Dr. Daniel Kaluka, PhD, em pesquisa de graduação sobre proteínas M em um parasita da malária, Plasmodium falciparum. Vincent é um jogador de basquete universitário da Taylor University e conquistou uma vaga na equipe acadêmica do Distrito 2 do NAIA em 2020. Depois de obter seu diploma de graduação, Vincent aspira a frequentar a Faculdade de Medicina e obter seu MD. Dedicação. Este livro é dedicado às dezenas de pessoas que me ajudaram e me inspiraram, especificamente meus pais, meu irmão, minha irmã e os professores da universidade e do ensino médio que ajudaram a tornar a ciência acessível para mim. O Novo Químico. Símbolo de copyright The New Chemist Publications 242, DJF. Seção 1. Fundações. A química orgânica é uma disciplina que exige esforço, foco e habilidade. Esses fundamentos foram selecionados após revisão guiada e observação de quais conceitos facilitam e dão suporte a um bom entendimento à medida que o aluno progride nesta disciplina de química. Esses fundamentos da metade aos metálicos destacam com foco conceitual, ideias-chave, pontos e auxiliares de memória para apoiar seu sucesso em química orgânica. Aprender química orgânica é semelhante a construir uma casa, requer tempo, habilidade e esforço persistente. Vamos começar. Desenvolvimento de conceito 1. Introdução. Objetivos. Aprenda as principais definições. Entenda as ideias-chave e a relevância das estruturas de ponto de Lewis. Entenda alguns conceitos simplificados da mecânica quântica. Moléculas orgânicas. Moléculas orgânicas podem ser definidas como múltiplos átomos associados ou ligados entre si, feitos principalmente de carbono. Em suma, as moléculas orgânicas são moléculas à base de carbono. Figura 1.1. Esta imagem mostra a estrutura da linha de ligação da cianocobalamina, também conhecida como vitamina. Essas moléculas podem ou não ter a mesma fórmula molecular. Nos casos em que a fórmula molecular é a mesma, mas a estrutura não é a mesma, isômeros estruturais. Alguns exemplos incluem acetona e dimetil-éter. Figura 1.2. Esta imagem mostra dois isômeros estruturais, constitucionais, acetona à esquerda e dimetil-éter à direita. A constituição ou conectividade não é a mesma, isômeros constitucionais. Observe que os isômeros mencionados anteriormente, constitucionais, às vezes são trocados pelo termo estrutural. O arranjo no espaço 3D não é o mesmo, estereoisômeros. Figura 1.3. Esta imagem mostra um par de enantiômeros, da esquerda para a direita, S-1 bromo 1 cloro etano e R-1 bromo 1 cloro etano. Subclasses de estereoisômeros. Isômeros ópticos são moléculas que giram a luz de maneira diferente e suas imagens especulares não são sobreponíveis, também conhecidas como enantiômeros, são normalmente designadas por E, Z, R ou S. Isômeros geométricos que são moléculas que possuem imagens espelhadas não idênticas, e o arranjo ao redor do plano da ligação dupla é diferente, ou seja, cis ou trans. Moléculas orgânicas podem ser lineares. A forma molecular linear é observada em HCN, cianeto de hidrogênio, ou acetileno, C2H2, ou ainda pode ser planar, mas trigonal, como o formaldeído, que é trigonal planar. Figura 1.4. Esta figura mostra as estruturas das linhas de ligação, da esquerda para a direita, de cianeto de hidrogênio, acetileno e formaldeído. Além disso, a molécula pode ter um arranjo 3D, como o metano, existindo como uma molécula tetraédrica. Figura 1.5. Esta figura mostra as estruturas das linhas de ligação do metano e do formaldeído. Explicação esquemática de moléculas e compostos. Figura 1.6. Esta figura mostra as diferenças e relações entre moléculas e compostos. A estrutura das moléculas 3D. A estrutura de moléculas tridimensionais, 3D, pode ser prevista usando uma aplicação de estruturas de pontos de Lewis desenhadas corretamente, que é chamada de teoria de repulsão de pares de eletrônicos da camada de valência, VSEPR. O VSEPR envolve a teoria da ligação de valência, mostrando todos os elétrons de valência e incluindo elétrons ligantes e não ligantes, em alguns casos chamados de pares solitários, e maximizando a separação no espaço 3D para minimizar as repulsões. Conectado à lei de Coulomb, em que uma distância maior minimiza o potencial de distribuições de energia para cargas iguais. O VSEPR é uma alternativa que pode informar e iniciar a jornada na compreensão da geometria molecular, sejam os alcinos lineares, os arranjos trigonais planares dos átomos de carbono em alguns alcenos ou os arranjos tetraédricos dos átomos de carbono em torno de alguns átomos de carbono nos alcanos. Outra alternativa envolve o uso da mecânica quântica, que usa funções de onda que são descrições matemáticas de distribuições de probabilidade de elétrons para produzir orbitais atômicos. Existem algumas limitações neste método no que diz respeito à precisão, como no método anterior, VSEPR, considerando as simplificações teóricas que são utilizadas. Em geral, o objetivo é obter uma melhor compreensão sobre o que ocorre na natureza. Por exemplo, com a mecânica quântica, podemos entrar na teoria da hibridização e usar a mistura matemática de funções de onda para aprofundar nossa compreensão do que é observado na natureza. Com o mesmo objetivo, através de ideias da teoria de ligação de valência, podemos prever os ângulos de ligação do metano. Especificamente no ângulo de ligação HH intramolecular no metano, são observados desvios, e a hibridação é responsável por esses desvios com explicações. Essas explicações implicam: arranjos lineares têm átomos de carbono que são sp hibridizados, um sp mais duas páginas S. Arranjos planares trigonais têm átomos de carbono que são sp2 hibridizados, um sp2 mais uma página. Arranjos tetraédricos têm átomos de carbono que são sp3 hibridizados, um sp3 mais 0 páginas. Outras hibridações ocorrem com menos frequência, na química orgânica convencional. Porém, com geometrias superiores comuns a compostos inorgânicos, pode ocorrer bipiramidal trigonal, sp3d, ou octaédrica, sp3d2. Nota: a mecânica quântica também envolve o uso da teoria do orbital molecular para entender outras interações, mas isso será discutido no apêndice. Com o mesmo foco, a mecânica quântica também permite que os químicos falem sobre densidades eletrônicas regionais, como ao longo do eixo internuclear, ligação sigma, ou ao longo dos eixos perpendiculares x, y, z, ligações π. Essas ideias podem ser aplicadas a arranjos de ligação, como ligações sigma ocorrendo em ligações simples, bem como ligações duplas com ligações sigma e uma ligação π. Além disso, em ligações triplas, existe uma ligação sigma e 2 ligações π. Questões. Fácil. O que é química orgânica e qual a origem histórica dela? Dica: Friedrich Wöhler em 1828. O que é uma classe de compostos orgânicos? Quais são os 3 tipos diferentes de isômeros? Médio. Explique a teoria da ligação de valência em termos gerais simples. Qual é um exemplo molecular em que a teoria da ligação de valência não explica com precisão o que ocorre nas moléculas? Duro. Quais são as hibridizações dos átomos de carbono no acetonitrilo? Quais são as designações de sigma e π para as ligações no acetonitrilo? Desenvolvimento de conceito 2. Grupos funcionais e outras ideias. Objetivos. Entenda o que é um grupo funcional. Compreender o formato-chave para a nomenclatura orgânica. Compreender o papel das forças intermoleculares, IMFs. Os grupos funcionais são partes características das moléculas, que transmitem propriedades químicas específicas às moléculas que as possuem. Grupos funcionais fazem inúmeras coisas, mas principalmente nos permitem compartimentalizar informações sobre moléculas, compostos e reações. Os grupos funcionais nos fornecem informações sobre as interações químicas, como as interações intermoleculares, bem como nos fornecem mais informações para entender as propriedades das moléculas. Isso inclui as propriedades físicas, pontos de ebulição e pontos de fusão, e solubilidades. Considerando a utilidade dos grupos funcionais, eles também possuem uma impressão digital molecular característica que é detectada de várias maneiras, principalmente em espectros, que serão discutidos em um desenvolvimento de conceito posterior. Desenvolvimento de conceito 6. Figura 2.1. Essas moléculas listadas acima transmitem diferentes atributos químicos e propriedades físicas para a molécula que possui essas porções. Da esquerda para a direita, hidroxila, sulfuridrila e benzeno, primeira linha, carboxilato, fenol, tiofeno, segunda linha, e furano, última linha. Tipos de moléculas e suas propriedades. Existem vários tipos de moléculas no mundo. No entanto, na disciplina de química orgânica existem moléculas específicas que são discutidas com frequência, incluindo estas. Alcanos. Alcanos, também conhecidos como parafinas, são hidrocarbonetos saturados e compostos alifáticos. Essas moléculas formam uma série de homólogos com uma unidade repetitiva de metileno, CH2, e com a fórmula geral CnH2n mais 2, e, terminando com o sufixo -ane. Por exemplo, em ordem crescente de 1 a 5. Metano CH4. Etano C2H6. Propano C3H8. Butano C4H10. Pentano C5H. Os seguintes prefixos são ex, 6 carbonos, ET, 7 carbonos, OCT, 8 carbonos, não, 9 carbonos, e DEC, 10 carbonos. Esses prefixos de MET, A, DEC, são aplicáveis em toda a nomenclatura de compostos orgânicos, alcanos, alcenos, alcinos, álcoois etc. Alcenos. Os alcenos, também conhecidos como olefinas, são hidrocarbonetos insaturados e são considerados compostos alifáticos. Contém pelo menos uma ligação dupla, formando uma série homóloga com a fórmula CnH2n. Essas moléculas terminam com ou sufixo N. Alcinos. Alcinos, também conhecidos como acetilenos, são compostos insaturados com uma ligação tripla. Estas moléculas formam uma série homóloga com uma fórmula geral de CnH2n2. Essas moléculas terminam com o sufixo -ine. Existem várias outras moléculas que têm uma série homóloga dentro de seus grupos, incluindo ácidos carboxílicos, CnH2n mais 1 CO, e aldeídos, CnH2n mais 1 CHO. Álcoois. Álcoois cujo principal grupo funcional para identificação é o grupo hidroxila ou é notadamente prioritário na prática de nomenclatura. Exceções incluem os ácidos carboxílicos, segundo a IUPAC. Os álcoois contêm uma ou mais hidroxilas formando uma série homóloga, CnH2n mais 1 ou. Álcoois são alifáticos e geralmente terminam com o sufixo ou. Forças intermoleculares e outras propriedades. Com os grupos funcionais vêm certas propriedades, como pontos de ebulição e pontos de fusão específicos, bem como temperaturas críticas, a temperatura em torno da qual um vapor não passa facilmente por uma mudança de fase para um líquido, e muitas outras propriedades físicas. No entanto, abaixo da superfície das propriedades físicas estão as características ou interações químicas conhecidas como forças intermoleculares que influenciam e permitem previsões comparativas e propriedades físicas. Ou seja, existem forças-chave a serem lembradas. Forças dipolo-dipolo. São forças que ocorrem entre moléculas, intermoleculares, com momento de dipolo ou constante de elétrica significativa. Essas moléculas também são conhecidas como polares. Essas forças intermoleculares, IMFs, são relativamente fortes. Uma versão relativamente mais forte dessa força é a força intermolecular da ligação H. Ligação de hidrogênio. A ligação de hidrogênio é uma força mais forte, às vezes chamada de forte força dipolo-dipolo. Este é um fator relativamente forte, alguns o consideram o mais forte, dos FMIs. Ocorre na água e outras moléculas com ligações de hidrogênio AN, ou OF, e com acento agudo ON dipolo. Isso ocorre entre íons e moléculas polares, por exemplo, com solvatação de cristais de cloreto de sódio em água. Forças de dispersão de Londres. As forças de dispersão de London ocorrem em todas as moléculas e são baseadas nas interações coulomбicas entre dipolos transitórios, em essência, temporários. Essas forças eletrostáticas resultam em interações transitórias entre as moléculas. Forças de Van der Waals. Agora, uma força mais fraca que consiste em dois tipos inclui a força de Van der Waals, que é discutida resumidamente aqui e mais detalhes podem ser encontrados em outros textos. Vale a pena notar que os IMFs e seus pontos fortes são baseados em grupos funcionais, estrutura química e tipos de ligações químicas nessas moléculas. Ligação química. Ligação covalente polar. A ligação covalente ocorre entre átomos com diferenças significativas de eletronegatividade. Especificamente, essa ligação ocorre com heteroátomos, que se refere a diferentes átomos não metálicos. Muitas vezes a escala de Pauling é usada como referência para intervalos para determinar o tipo de arranjo de ligação que ocorre entre os átomos. Se ligar. Embora considerado uma construção teórica em alguns casos, é visto em um espectro, a ligação covalente polar existiria no meio. Ligação covalente. Isso está quase no outro extremo do espectro de ligação, onde há uma diferença menos significativa na eletronegatividade. Iônico. Isso está na outra extremidade do espectro de ligação. Isso ocorre entre metais e não metais. Por exemplo, no cloreto de sódio, há uma grande diferença de eletronegatividade. Resolução. A solvatação depende de muitos fatores, incluindo o princípio semelhante dissolve semelhante e ideias como hidrofilicidade e hidrofobicidade. Hidrofilicidade e hidrofobicidade. Esses termos referem-se à postura das moléculas em relação à água, se ela tem uma afinidade significativa com a água, hidrofílico, amante da água, ou uma afinidade menos significativa com a água, hidrofóbico, ódio da água. A tendência das moléculas é a seguinte: compostos polares e iônicos tendem a ser hidrofílicos, em comparação com compostos covalentes e apolares que tendem a ser hidrofóbicos. Nomenclatura. A nomenclatura de acordo com a IUPAC é baseada em 4 partes principais. O prefixo normalmente denota o número de cada substituinte ou anexo, S, de grupo funcional. Os prefixos incluem di, tri, tetra. O localizador, que é o número que descreve a ligação do grupo funcional ou a posição dos substituintes. 3. A cadeia principal, normalmente é a cadeia contínua mais longa da molécula. O sufixo é baseado no grupo funcional que preside ou priorizado, cadeia ou arranjo de ligação, ou seja, simples, duplo ou triplo. Os sufixos são tipicamente clássicos na terminação, com, ano, alcanos, eno, alcenos, ino, alcinos, amina, amina, amida, amida, oico, ácido carboxílico, ato, ésteres, uan, cetona, deide, aldeído. Fato importante a ser observado: o grupo funcional do álcool, hidroxila ou, normalmente é priorizado em geral. Substituintes são transcritos ou delineados no nome com base na ordem alfabética relativa, então, etil antes de metila e esse padrão continua. Ideia geral-chave, prefixo locante parenchain sufix, geralmente. Qualquer elaboração adicional será discutida mais adiante no texto. Questões. Fácil. O que é um grupo funcional e cite vários exemplos de grupos funcionais? Dica: O. Quais são os 3 tipos de moléculas orgânicas? O que é uma força intermolecular? Médio. Explique as forças dipolo-dipolo. O que é um exemplo molecular, onde as forças intermoleculares explicam uma propriedade física, como o ponto de ebulição? Duro. Qual é a diferença entre a ligação de hidrogênio e as forças de dispersão de London? Explique o processo geral de nomeação de compostos orgânicos simples. De conceito 3. Estruturas, conformações e projeções. Objetivos. Compreender e ser capaz de desenhar estruturas de pontos de elétrons de Lewis, estruturas condensadas e estruturas de linha de ligação. Compreender e ser capaz de desenhar diferentes conformações, principalmente as do cicloichano. Compreender e ser capaz de desenhar e identificar projeções de Fischer e projeções de Neumann. Estruturas. As estruturas são representações esquemáticas de diferentes moléculas e fornecem um meio de compreensão do que está ocorrendo na natureza. Há uma variedade de estruturas diferentes usadas na química. Os principais exemplos na discussão a seguir serão estruturas de pontos de elétrons de Lewis, estruturas condensadas e estruturas de linha de ligação. Estruturas de pontos de elétrons de Lewis. As estruturas de pontos de Lewis são construídas com base em algumas ideias-chave, como a valência do átomo e a regra do octeto. Há também exceções específicas para o período 3 e além. Valência. Valência refere-se à quantidade de elétrons que um átomo perderá, muitas vezes resultando em um I com acento agudo ou N carregado positivamente, cátion, ganho, muitas vezes resultando em um I com acento agudo ou N carregado negativamente, anion, ou compartilhado, normalmente ocorrendo em moléculas covalentes para ter uma configuração estável de elétrons de gás nobre. A valência pode ser determinada usando a tabela periódica. O número do grupo, números da coluna vertical na tabela periódica é designado como valência. Essa valência normalmente corresponde à carga, ou número de oxidação, e seu sinal subsequente depende do tipo de átomo, sua reatividade e com o que está reagindo. Um ponto-chave a ser observado. A valência pode ser mostrada rapidamente usando estruturas de ponto de Lewis e o arranjo orbital pode ser explicado simplesmente, embora não seja completo em precisão, usando o modelo de Bohr. O modelo de Bohr envolve o uso do símbolo atômico cercado por círculos representando o orbital do elétron com pontos simbolizando os elétrons. O modelo de Bohr, de certa forma, coincide com a configuração eletrônica do átomo. Regra do octeto. A regra do octeto é um princípio com aplicações em teoria da ressonância, mecanismos químicos simples e reações. A regra do octeto é baseada na ideia de átomos ganhando, compartilhando ou perdendo elétrons para ter um octeto completo, 8 elétrons externos. Há exceções, por exemplo, alguns átomos podem perder elétrons para possuir a configuração eletrônica de hélio, 2 elétrons externos. No entanto, para a maioria dos átomos no período 1 e período 2 na tabela periódica dos elementos, esses elementos obedecem à regra do octeto em geral. Essa regra é útil para prever a reatividade e explicar simplesmente o motivo de certas reações químicas. Exceção específica para o período 3 em diante. Dependendo do átomo, sua reatividade e com o que ele está reagindo, há exceções à regra do octeto. Por exemplo, com certos átomos metálicos como alumínio, Al, e outros, incluindo ferro, não metais como fósforo e selênio e gases nobres como xenônio. Existem muitas exceções, mas a regra ainda fornece uma estrutura para o desenvolvimento conceitual. Método para escrever estruturas de pontos de elétrons de Lewis. Para átomos e íons. Para átomos e íons, considere principalmente o número do grupo e a configuração eletrônica. Por exemplo, a estrutura de pontos de elétrons de Lewis do cloro ou do hidrogênio. Figura 3.1. A figura acima mostra as estruturas de pontos de elétrons de Lewis de um átomo de cloro e um átomo de hidrogênio, da esquerda para a direita, respectivamente. Para moléculas. Comece determinando a contagem total de elétrons entre os átomos da molécula. Em seguida, desenhe ligações simples entre cada átomo. Subtraia 2 elétrons, para cada ligação simples, do elétron total. Contar. Adicione ligações extras quando necessário, por exemplo, para ligações de oxigênio de carbono em aldeídos e cetonas, o arranjo de ligação normalmente está na forma de uma ligação dupla. Conheça e observe as tendências. Após todas as ligações extras necessárias terem sido indicadas, subtraia a quantidade correta de elétrons para as ligações extras adicionadas. Normalmente, com os elétrons restantes, denote-os como pares solitários, em torno dos átomos relevantes. Estruturas condensadas. Estruturas condensadas são importantes no processo de compreensão do que as estruturas de linha de ligação representam e mostram. Em estruturas condensadas, todos os hidrogênios são mostrados ligados aos carbonos, por exemplo. Figura 3.1b. A figura acima mostra a estrutura condensada do S-2-bromo-butano. Estrutura da linha de ligação. As estruturas de linha de ligação são o próximo passo depois das estruturas condensadas. Estes mostram apenas a estrutura de carbono com cada carbono representado por uma dobra na cadeia e o hidrogênio não denotado, mas inferido ou assumido, até o ponto ou um octeto completo ao redor do átomo de carbono. Isso significa que os hidrogênios não são mostrados, mas implícitos até o ponto em que a valência do carbono é satisfeita. Por exemplo, sinal igual a. Figura 3.2. As estruturas acima mostram a estrutura da linha de ligação do butano, sob a qual está a estrutura condensada do butano. As estruturas de linha de ligação são úteis e eficientes. Observação. Na descoberta da estrutura do benzeno, ciclohexatrieno ou ciclohexatri 1,3, 5-eno, August Kekulé determinou uma estrutura de uma molécula de anel de 6 carbonos com ligações simples e duplas alternadas. Esta estrutura, vista abaixo, é um bom ponto de ramificação de estruturas condensadas para estruturas de linha de ligação. Sinal igual a. Figura 3.3. A figura acima mostra, da esquerda para a direita, uma versão da estrutura Kekulé do benzeno e a estrutura da linha de ligação do benzeno.
Thanks for listening. We're glad you were able to tune into this podcast. Once again, this is the New Chemist, where we discuss chemistry, which simply put is the science of change, as well as the other sciences, careers, community, research, and COVID-19. Thanks again for listening. Note, the views on this podcast represent those of my guests and I.